Hello children, today we are going to discuss about electric field. So from the previous class, we have learned about Coulomb's law. We know that when two charges are brought in contact with each other, they experience a force. That is, you take two charges Q1 and Q2 which are placed at a distance r apart. There is a force experienced by these two charges and the magnitude of the force is calculated by F is equal to K into Q1 Q2 upon R square. This is Coulomb's law. So now I am bringing one single charge here. Okay. I don't have two charges. Now I am bringing only one single charge. Okay. So let us take this charge as Q here. Okay, we'll erase this. Let us take a single charge Q here. Okay. So now will we experience any force when only one charge is present? No. Okay. So now I am bringing another small charge closer to this charge Q. At a particular point, from a particular distance, we will experience a force of repulsion or attraction based on the nature of this charge. This repulsion or attraction is due to the fact that this charge is experiencing a force on this charge. Unless and otherwise we bring this charge, we don't experience any force there, right? So the region where the force of this charge is experienced is called the electric field. Okay. So the region wherever you experience the force of this capital Q is called, this will be like, no, it will be to a vast area. So now say for example, if this charge Q is in a place somewhere here, okay, where there is no field, where there is no force, where there is no like influence of this greater Q, will we experience any force? No, we will not experience. Only when we try to move it closer to the charge capital Q, we experience a force. So the region where we are experiencing the force is called the electric field. Okay, or electric field intensity. So electric field or electric field intensity is the region around the charge where you experience the force. And this force can be experienced only when you bring a other charge near this charge, or only when you try to bring another charge near to this charge. Okay. So now if we see the definition of this electric field or electric field intensity due to a charge capital Q at a point in space. At a point in space may be defined as the force. It can be attractive or repulsive, as I told you earlier, based on the nature of the charge. Now there is a word called unit positive charge. What do you mean by this unit positive charge? So unit positive charge means nothing. The nature of the small q will be much lesser than the value of capital Q. Okay, capital Q, the magnitude of the charge possessed by capital Q will be much, much greater than this small q, such that when you place this charge near the, when you bring this charge closer to capital Q, this capital Q charge, that is the bigger Q charge, will not change its position. It will only exert a force, but the position will not be altered. Okay, so this small q will be of very small magnitude. It is like, see, for example, you are sitting in your classroom. Okay, a LKG child is coming and pushing you. Will you fall? No. But you will experience that force, right? Yes. So there will be a force experience, but there will be no change in the position of the charge. So that is the case. That is an example taken to explain unit positive charge. Unit positive charge means it is a very, very small charge. So when you bring this unit positive charge near this capital Q charge, what happens? There is a force experience, but there is no impact on the charge that is producing the force. Okay. So now here you can see two diagrams which represents the electric field. This is electric field from an isolated positive charge. By positive charge, you can see that the field lines are directed outwards radially in all directions. That means the symmetry possessed is spherical symmetry or radial symmetry. In both of them will be correct. Now here you can see there is a negative charge. As you can see, the field lines here also, the field lines are shown around in spherical symmetry. One difference you can observe here, the field lines are directed outwards and here the field lines are directed inwards. This is the property of field lines which we will be studying in the next class. But as of now, for a positive charge, field lines will emerge radially outwards, and for a negative charge, field lines will be directed radially inwards. Okay. For a positive charge, listen carefully. Field lines will be directed radially outwards, and for a negative charge, the field lines will be moving towards the negative charge, that is radially inward direction. So the charge that is producing the field is called the source charge. Okay. Source charge, and the charge that is experiencing the field and the associated force. Field and force, not only field and the force also. That is called the test charge. So test charge is a charge used for testing. It is in very, very small magnitude compared to the source charge. The reason why we choose this is for experimental purpose. We do not want the orientation or position of the source charge to be disturbed. We wanted to check only the magnitude of the force that this test charge is experiencing due to the source charge. Okay. So with this, we will move to the mathematical understanding of electric field intensity due to a point charge. Whatever we saw earlier only, we are going to see it mathematically. Take a source charge Q. So here you can see, as you saw earlier, there will be field lines in all directions. Okay. Now I am bringing a test charge Q here. So this test charge, this is also positive I will take. So this test charge is getting repelled due to the source charge, due to the field lines of the source charge. So that is what described here. This is a very big line. For your understanding, this like it is not necessary, only single lines are enough. Okay. So this capital Q is the source charge. When I bring this is the field of the source charge. This region is the field of the source charge. Now I am bringing a test charge. So this is repelled in this direction. That is what F. This is a vector. Okay, force is a vector. So now, according to Coulomb's law, the force between these two can be calculated as you all know from the previous class, 1 by 4 pi epsilon naught Q into Q divided by R square. And this R is the direction vector which indicates the direction of the R cap. R cap is the direction vector which indicates the direction of the field lines. Okay. Now, if you will see here, carefully observe this test charge, you can take it outside and you can write the source charge and the remaining parameters together. That is small q into capital Q by 4 pi epsilon naught R square into R cap. So this quantity, okay, this quantity, you can write it as the quantity of electric field. Okay. So this is the quantity of electric field. So you can write the force experienced by the unit charge F as F vector is equal to Q into E vector, where E is nothing but capital Q divided by 4 pi epsilon naught r square r cap. Okay. So from this, how will you write E? E will be equal to F vector divided by Q. Now I have already told you the value of Q should be extremely small such that it does not impact the source charge. Okay. So now here electric field we have written, and we have written E is equal to F by Q. A new term is added, limit Q tends to 0. That is, the test charge Q should be negligibly small such that it does not disturb the source charge. Okay. Now the SI unit of electric field intensity. You know that the SI unit of force is Newton, and for charge it is Coulomb. So it will be Newton per Coulomb. And there is one more SI unit which is volt per meter. So this comes from the next chapter, electrostatic potential. So we will be discussing about this unit when we discuss that chapter. Okay. There is a formula V is equal to E into D. From there this comes. We'll be discussing this during the next chapter. And electric field intensity, as you know, is a vector quantity because obviously force is a vector. So field will also be a vector quantity. So now what is the significance of this electric field? So now you know that there is a test source charge. This is experting a field in all directions. Okay. Now, if I bring a test charge, the force experience at this point will be different. At this point will be different. At this point will be different. So at each and every point, the force experienced by this test charge will be different. It will be varying, keeping on varying. He always varies from point to point. That is, as we move towards the charge, what will happen? The field will increase so that the amount of force exerted over the test charge or the amount of force experienced by the test charge will be greater. The electric field, this field is the example of vector field. Okay, so everywhere there is a unique vector. You can draw any number of vectors from the center indicating the direction of the electric field. So now the source charge Q produces a definite field. That is, at each point, the field is existing and it is decreasing as we move away from the charge. Okay. So the value of electric field at any point in the region surrounding the source charge will help us determine the force experienced by the test charge. Okay. Based upon the field in a particular region only, the force exerted to the test charge will also depend upon. The electric field is an important quantity that will tell us how much force the test charge can experience due to the source charge. Okay. So now with the understanding of what is electric field and how the force is experienced on a test charge due to the presence of source charge, we are moving to the next advancement of electric field due to a system of charges. You know, system of charges means there are more number of charges. You can see here there are 4 charges, Q1, Q2, Q3 and Q4. Distance between Q1 and at this point we are going to calculate the electric field. Okay. Distance is taken as R1P, R2P, R3P and R4P respectively. Okay. So now Coulomb's law also we calculated. Force between multiple charges we calculated. So there what we did was we calculated on a particular charge the force experienced by Q1 due to the presence of all the other charges. Here the field experience at a particular point. Okay. Field experience at a particular point. What you have to do? You have to add up all the field that is present in that point by applying superposition principle. Okay. So superposition principle for a force we saw the earlier. Now you can see for a field, the electric field, I'll write it here. Superposition. So the electric field at any point due to a group of charges is equal to the vector sum. Vector means because it is having a direction, right? Vector sum of the electric fields produced by each charge individually at that point. So, the electric field at any point due to a group of charges Q1, Q2, Q3, Q4 will be equal to the vector sum of each charge produced individually at this point. So, we have to just add it by vector addition. Okay, we'll see the example. So, now we are taking the electric field E1 at R due to Q1 at R1. So now here there is a small change. This point is taken as R. Okay. So it is 1 by 4 pi epsilon naught Q1 divided by R1P square into R1P cap. Similarly, for the second charge, you have to write E2 is equal to 1 by 4 pi epsilon naught Q2 by R square 2P R2P cap. Okay, so now for n number of charges, what we will do? We will add it till Rnp cap. E1 R, E2 R, plus etc. up to ENR. Okay, this is the superposition principle. You are vectorically adding everything. So now summation. In the last class, I hope you remember that I wrote the counter from 2 to n because I took charge Q1 outside. Q1 is same because we calculated the force on Q1. But here it is not like that. For each charge, you have to calculate it separately. So the counter starts from I is equal to 1 to n. Please remember this. So Qi divided by R IP square into R IP cap. This is a general expression for electric field due to a combination of charges or due to multiple charges. Compare with Coulomb's law and study so that you are able to understand the differences. It is nothing. There the counter starts from 2. Here the counter starts from 1. Okay. This is the general expression for electric field due to multiple charges at a particular point. So at a different point, you have to add the electric field due to all the charges at that particular point. Okay. Now we will test our understanding. We are taking two charges, plus 1 microcoulomb and plus 4 microcoulomb at a distance of 30 centimeter apart. So how far from the plus 1 microcoulomb charge on the line joining the two charges will the net electric field be 0? So you have to draw the diagram first so that it is easy for you to solve the sum. So draw the diagram, take two charges, take two points A and B. So and we are placing charge Q1 is equal to 1 microcoulomb here. Q2 is equal to 4 microcoulomb here. Okay. And we wanted to calculate the point from Q1. You have to check at what point the net electric field will be 0. Okay. So we'll take that point O. So now the total distance is 30 centimeter. Now, please understand carefully. If this distance is X, this distance will be 30 minus X. Very good. Okay. So now, at this point O, what should happen? The value of EA plus EB should be equal to 0. Electric field at this point should be equal to 0. That is, modulus of EA vector should be equal to modulus of EB vector. Okay, this is vector symbol. And the direction of EA and EB should be mutually opposite to each other. Okay. So now equate both EA and EB. You will get 1 by 4 pi epsilon naught Q1 by X square. Because here it is field, only one charge will be involved. Don't get confused with Coulomb's law force. Okay. So here it will be Q2 by 30 minus X the whole square. This will get cancelled. This will get cancelled. So what is the value of Q1? 1 microcoulomb by X square will be equal to 4 microcoulomb by 30 minus X the whole square. Correct? Okay. So now bring this side. You will get 30 minus X the whole square divided by X square will be equal to 4 microcoulomb divided by 1 microcoulomb. Micro will be 10 power minus 6, which is common in both denominator and numerator. So it will get cancelled. Now you will get it as 4. So now (30 minus X the whole square divided by X square will be equal to 4 by 1. Now cross multiply. You will get it as 30 minus X the whole square is equal to 4X square. We need to find out X, right? So what we will do is we'll take square root. So you will get it as 30 minus X is equal to 2X. Because 2X the whole square is 4X square. Now bring this X this side. You get 30 will be equal to 3X. So X will be 30 by 3 equal to 10 centimeter. So this is the distance at which the electric field is equal to 0 from the charge 1 microcoulomb. You have to solve a number of sums. Numericals are very important for you to get good score. So keep practicing numericals this way. We will be uploading additional numericals with relevant to the topics after the completion of the theory part of the chapter. In the channel, keep watching. Any questions or difficulties you have, you can share in the comment section. We are happy to help you. Thank you.